Hello everyone, this is Brock Skaggs, and to make this video where we're going to look into drawing the shear force and bending moment diagrams for the beam you see before us. And so it's a simple supported beam. You can see a pin joint on the left hand side at A, a roll on the right hand side at B. Overall length is going to be 12 meters is the way to interpret that. And we've got a distributed load, more specifically a uniform distributed load with a value of 1,000 newtons per meter over the first 2/3 of the beam's length there. And so we're going to use somewhat of an inspection method where we'll basically determine the reactions first, and that's I've actually already done, so we can focus more on the relationship between shear and bending moment diagrams. Then we'll make sketches of the shear and bending moment diagrams, and finally use some relationships as far as knowing how the externally applied load, in this case the distributed load, is related to the shear force, and how the shear force is relating to the bending moment to help us come up with piecewise defined equations in this sense in order to describe the internal shear force and the internal bending moment at any given point along the length of the beam itself. And so with that being said, let's go ahead and hop right into the solution. And so I'll just kind of zoom out a little bit here. First step was to determine the reactions. In order to shorten this video a little bit, I've went ahead and written out the free body diagram as well as equilibrium equations. And so just walking us through the steps here, first think of the reactions. If I make my free body diagram, the entire beam itself would separate it from the reactions at A and B. A is a pin joint, so I'm representing it by two components of the force that pin is going to be able to exert on the beam itself. And that's why I've got A sub x and A sub y there on the bottom left of my beam. And then on the far right hand side, I've got the roller that's rolling on a horizontal surface. And so here we know that the reaction force is going to be perpendicular to the surface that the roller is sitting on. And so that's going to be just a strictly upward reaction, B sub y there. And then for the distributed load, well, that distributed load is a distributed load in of its sense. But what you might notice is, hey, I've moved it from a distributed load to a concentrated force here, and so that's okay. Basically all I need to do is make sure that it is statically equivalent to the actual distributed load. And so the way I've been able to do that is, as far as the magnitude goes, I need to have the magnitude equal the area under the distributed load curve. And so in this case, the distributed load curve just forms a rectangle, right? You can see the 1,000 newtons per meter, think of that as the height, and then the base is just the 8 meters that it covers. And so then I can calculate that area. It ends up being 8,000 newtons, and that's what I'm calling the capital W there, which is the statically equivalent point force. Then it's just a matter of, okay, where do I place this statically equivalent point force along the length of the beam? And the idea is that you place it at the x-bar location, or the centroid location, or horizontal coordinate of the centroid to be more specific, associated with this distributed load area that's being bounded by the curve. In this case, the curve is just a straight line, a constant 1,000 newtons per meter, and so essentially we're at half the base of that rectangle, so in this case 8 over 2 or 4 meters. So with that being put in the free body diagram, then I simply wrote my equilibrium equations, which you're seeing here, and came up with the values for A sub x, A sub y, and B sub y. So it turns out that B sub y is equal to 2,666 2/3 of a Newton pointing upward. A sub y is 5,333 1/3 newtons pointing upward as well. And A sub x is going to 0 at this point. So with that being done, now we're ready to move on to the shear diagram. And so that'll be our next order of business. And so get the pin going, and we'll need a spot here so we can talk about the V as a function of x, which is the shear plot. And so first I'll go ahead and draw some coordinate axes here. And rearrange a little bit, just like so. And so as far as what this is going to be plotting, we're going to have the shear force in newtons, and we'll have the position along the beam, length of the beam, x in meters here. And so using the inspection method, we say, well, at the far left hand side we've got a pin joint, so that will cause no moment, but it's going to have a discontinuity here associated with the shear force. It's not going to start at 0, but it's going to jump up automatically by this magnitude associated with A sub y here, which it appears to be 5,333 and a third newtons. And so we'll go ahead and just place that, say, here. So automatically it's jumping up by the magnitude of the reaction force associated with the pin and going to roughly 5,333 newtons. And then we think, okay, what happens as soon as we start walking along the length of the beam? Well, we think about the forces, what forces are going to be exposed themselves to the beam. And so right off the bat, we have this distributed load. And so the distributed load is going to cause a gradual change in the shear force. In this case, the distributed load is directed downward, so it's going to be a dropping effect here. And essentially, by the time we get to 8 meters, it's going to have dropped the entire magnitude of the distributed load itself here. And so one can think of it that way if they'd like. Basically what you have here is the 5,333 and a third newtons minus 8,000 newtons. And so what that's telling me is by the time I get to the x equals 8 meter mark, which is when the distributed load is finished, my shear force is going to have dropped all the way down, say it's right here, to negative 2,666 and 2/3 of a newton. And again, the magnitude that's dropping is going to be equal to the magnitude of that statically equivalent point force here. How about we try to make an actual line? That might give us a little bit of luck. There we are. And so there's our line. One of the relationships that we'll talk about more in a later video is something like dv dx is equal to negative w. And if I kick the dx to the other side, say dv is equal to negative w dx. This negative w dx, you can almost think of that as the area, that's the rectangle associated with our distributed load, and that is equal to the change in the magnitude of the shear force here, which is basically what we've been talking through as we drew this line. As far as how did I know it's a line being drawn here, because originally I just said, hey, I've got to go from the point 0, 5,333 roughly, to 8, negative 2,666. Well, I can think of it this way. dv dx is negative w, or I could look at it one other way as v is equal to negative the integral of w of x dx. Here starting to talk about some of the relationships that are happening between the internal shear force and the distributed load. Well, if I think of the integral portion here, I've got a constant value for w as a function of x, right? It's just a constant 1,000. If I integrate that, I'm going to get to a linear function, and the negative sign out here is going to cause it to be a negatively sloped linear function, which is exactly what this line is representing. So now we've got the first portion of the shear force diagram made between 0 and 8. But what happens after we get past 8? Well, between 8 and 12, or right before I get to 12 at least, there's no forces at all on the beam itself. So that's going to translate to me just having a constant value of the shear force until I get to 12. Once I get to 12, though, what happens? Well, I've got b sub y, right, pushing upward here with the magnitude associated with the upward reaction of the roller. And so b sub y here is 2,666 and 2/3, which is exactly where I'm at. So it's going to get me right back up to the x-axis, which is what I was expecting. So that is the shear diagram. Since we've already got a little bit of work done here, let's go ahead and write out the piecewise defined equations. And so hopefully you can see here that there's going to basically be two descriptions of the shear diagram, right? One between 0 and 8, which is going to be this negatively sloped line, and the other between 8 and 12, where we just have the constant. And so that's why we need a piecewise defined description for the internal shear force. And so here's my v of x over the first part of the beam. We've got to basically come up with the equation of this line. Well, one thing that'll help us are these mathematical relationships. And so dv dx is equal to negative w dx, or probably more appropriate in here, dv dx is equal to negative w here. Basically we're saying is the slope at any given point on the shear diagram is equal to opposite of whatever the magnitude is at that point of the externally applied load, or excuse me, the distributed load, if you will. And so this distributed load magnitude is a constant value, 1,000, and so what this is telling us is the slope of this line is equal to negative 1,000. And so negative 1,000 here, that's the slope, so it's times x. And then what's the y-intercept? Well, we can read that right from the graph that we've already made. That's the 5,333 and a third. So negative 1,000x plus 5,333 and a third is the equation of this line. And notice how knowing these mathematical relations helped us to very quickly obtain that. And really all I would suggest doing is kind of memorizing the top one here, that the first derivative with respect to x, the positional length of the beam, of the shear force is equal to the opposite of whatever the distributed load value is at that given point. And so need to put in the domain that this is good through. 0 is less than x, which is less than or equal to, we'll say, 8. Here this is in meters, so if I want to make a note to myself, my x is going to be in meters and my v is going to come out in newtons here. And so we've got this sharp discontinuity happening here at x equals 0, associated with the concentrated force A sub y, and then at B there's no concentrated force there. That's where I'm putting the less than or equal to. So what about the period between 8 and 12? Well, it's just a constant, right? Negative 2,666 and 2/3. Negative 2,666 and 2/3. And that's between 8 and 12. Again, at 12, we got that upward reaction A sub y, or excuse me, B sub y, associated with the roller. And so that's looking pretty good. The only other thing that I would like to add is to determine where it crosses the x-axis right here, because that'll be an important point when we start talking about the bending moment diagram. And so I'm wanting to know, okay, where does this occur? X equals 5, x equals 6, x equals 7, so on and so forth. Well, it's easy enough to do that because we know the equation of the line. V1 of x, if you will, is equal to negative 1,000x plus 5,333 and a third. Well, if I just set that equal to 0, I should be able to solve for x. And so here we'll do that. I'll just write here, solve for x-intercept. And it'll take 0 for the left side of v1 as a function of x. That is negative 1,000 times x plus our 5,333 and a third. Here I can just solve for x. You can see it's going to be the 5,333 and a third divided by 1,000. And you end up with 5 and a third. So this crosses the x-axis and goes from a positive value for the internal shear force to a negative value of the internal shear force at 5 and a third units away from the left-hand side, or point A is what we called it. And so with that, everything's looking good for the shear plot. At this point, I could basically have anybody ask me a question as far as what is the shear force at any point x between 0 and 12, and I could immediately tell you, okay, x is this value using our nice piecewise defined equations. And so that's looking good. Next, let's go ahead and go to the m of x plot. And so let's investigate how the internal bending moment is changing along the length of the beam. And so m of x plot will work down here. Same idea as far as setting up my axes. I'll make sure we get the entire thing there. Alright, and so here we'll have a m value. And this will be in Newton meters for the unit and an x in meters. And so we're using this inspection method. First thing I'm going to think about is, well, I got a pin joint here at A. It cannot support a moment, and so I know it's got to start at 0, 0. And then I have a relationship here that I remember, and it's basically that there's an integration that's going to be happening. One way to think about it is the derivative of the bending moment with respect to x is equal to v, or to show the integration of it, it's m is the integral of v of x dx. We'll probably have to use this form in order to come up with the equations. But here, if I'm integrating between here and here, I'm going to have not just a graph with lines on it, but there's going to be some curves on here as well, right? I'm going to have a parabola that's going to actually develop from a shear function that is a linear function. But before we get too carried away, one thing we can think is, okay, between 0 and 5 1/3, the bending moment has to increase by the area of this triangle here. It's one of the more basic ways you can think about this integration is that, that the amount that the bending moment is changing between 2 points along the length of the beam is equal to the area under the distributed load curve between those same 2 points. And so here I'll just kind of line these up as best I can. There's 5 1/3, here's 8, and here's 12 over here. And so one way we can look at this is splitting this thing into 3 areas. You've got area 1 here. If I kind of split this part off here, area 2 here, and area 3 here. And so one way to look at this is, well, let's calculate the 3 areas now. And so you've got area 1 is going to be 1/2. The base is 5 1/3. And the height is going to be the 5,333.3. Here I left off the units, but this is going to be in meters, and this is in newtons, so this should give us a value in Newton meters. And so I'll just quickly grab my calculator and enter that in. It looks like 14,222.2 Newton meters is the amount that it's going to rise. And then area 2 next. That'll be 1/2. Here we'll have 8 minus 5.3. Essentially, I'm just trying to figure out this leg right here of the triangle number 2. And then this height, if you will, is going to be a negative value. It's going to be negative 2,666 2/3. And we'll calculate that one as well. Negative 3,555.5. And finally, our area 3 is just a rectangle. And so here, that third area, 8 minus 12, that's 4 meters for the base, and then the height is again that negative 2,666 2/3 there. Negative 10,666 and 2/3 as well. There we go. And so what we've basically done is determined the amount that the bending moment is going to change between different x points. One of the things to take note of is that there's no externally applied moments, either reaction moments or moments that would come from externally applied loads on this beam itself here. And so one nice thing about that is I should be able to sum these areas up, and they should sum very close to 0. Maybe some rounding a little bit with just the way the calculator is working, which is basically what mine's saying. I get negative 1 times 10 to the negative 9th values, but essentially think of that as 0. And so what that's telling me for area 1 is that I'm going to start at 0, 0, which we've already talked about because of the pin joint, but by the time I get to 5 1/3, I've got to obtain some value, say it's about this high here, and that value is going to be 14,222.2. But then as soon as after I leave, I'm going to start decreasing here. That's why we got a negative area for area 2. And so by the time I get to 8 meters, I'm going to have to drop off the amount of that area 2 triangle. And so what I can do is take that 14,222, add the negative 3,555 and some change there of area 2. That gets me down to another value, which will be, say, here, with a magnitude of 10,666 and 2/3 of a Newton meters there. And so I've got these 3 points. You can see my first point at the origin, here's this point at the very top, and a point that's a little lower at x equals 8. And how do we connect all these? Well, this is where it helps to remember the mathematical relationships here as far as integration. And so I'm integrating a linear function. There's going to be some squared terms in the result, so it's essentially a parabola. And here it's going to be a downward facing parabola, if you will, that's going to connect those, something like that. One way you can know it's downward facing is you can see, if you think of Calc 1 stuff here, initially the slope's going to be a large positive number, and it's going to decrease until we get to x equals 5.3 meters where it levels off. And so here my line's going to start off quite high as far as the slope, and then it's going to gradually taper off there as I move from left to right. And so that gets us a picture, if you will, a graph of the bending moment over the first 2/3 of the beam. But what about the last third here from 8 to 12 meters? Well, I'm integrating now a constant, and so I'm going to have a negatively sloped linear function. The amount that it's going to drop between 8 and 12 is equal to the area that I've got dubbed as area 3. That's negative 10,666 and 2/3. Well, I'm at 10,666 and 2/3 there, and so it's just going to basically be a straight line going from x equals 8 to x equals 12, and it's going to connect those 2 points. Again, it makes sense at x equals 12 that I've got no moment there, because remember the reaction is just a roller, and so it's not going to be able to support a concentrated moment. And so it's a little bit messy here the way I've drawn it, but basically you have a parabola from between x equals 0 and 8, and then you've got a straight line between 8 and 12. Okay, so next the only thing that's left to do is come up with the equations, descriptions of the bending moment as we walk along the length of the beam. And here, especially on the parabola, it's very important that we remember this relationship, or else it's going to be very difficult to solve for the equation of that. And so let's start with that. And so one rule I know is that m is equal to the integral of v of x dx. And here I'm going to put a subscript 1 here, and this will be m1 as a function of x, because I basically have m1 that's going to run from 0 to 8, and then I'll call m2 the description between 8 and 12. And so just filling in what I now know, we've got the integral here. Well, what is v1 as a function of x? Well, that's exactly what we solved for here. It's the negative 1000x plus the 5333 1/3. And so we'll just substitute what we know. Okay, remember our dx. This is an indefinite integral, so we'll go ahead and perform the integral. So that would be negative 500 times x squared plus the 5333.3x, and we're going to have some constant c1 here. So what is the c1 value? Well, here we have to know something about this m description in order to come up with that c1 value. Just know the bending moment between 0 and 8 at some point, and we're good. I usually like to look at my reactions if I can, and so one of the things I've been talking about a little bit is the fact that, hey, I've got at x equals 0, or at point A, a pin joint. The pin joint can't hold a moment, so I know that the internal bending moment's got to go to 0 at x equals 0. And so here I can say, hey, my known point is that m1 at x equals 0 is equal to 0 there. And so I can use this relationship to solve for c1. That would just be something like 0 for the left-hand side, that's this 0, is equal to negative 500. Now every time I see an x I put a 0. And what you'll quickly be seeing is what this causes is C1 goes to 0, right? This term goes to 0, this term goes to 0, and we've got 0 is equal to C1. And so now we've been able to determine what that integration constant is. And so it's a little messy at this point, but we've essentially determined what the equation is for this parabola. And we'll write it a little nicer in a nice piecewise defined format a little later on. But now we've got the line here on the right-hand side. Well, using this relationship here, dm dx is equal to v. Dm dx is going to be the slope of the line, and that's equal to v. And so I'll put in red here. Well, I know the slope of this line is just equal to the v value between 8 and 12. And it's just a constant, so it's negative 2,666 and 2/3. And that's a lowercase m just to make sure nobody gets confused. And so now that I know the slope of the line, I can think, well, a line is mx plus b. And so m2 as a function of x is going to have the form negative 2,666.6 times x plus some b value. I'll call it C2 here. And so again, the problem at this point is to figure out what is C2. Well, here again you have to know a point. Some point on the line would be good. Here the easiest point is probably the right hand side, right? At x equals 12, I know that this expression's got to go down to 0 because of the roller. And so I'll put known point is that m2 at x equals 12 must equal 0. And so here I've got 0 is equal to negative 2,666.6 times now the x goes to 12 is C2. And we solve for our C2 value. And so just give me one moment. And that appears to be 32,000. And so that gets us the 32,000 for the y-intercept there. So at this point, let's go ahead and make it a little neater. We've got all the answer here, but it's just kind of all over the place, if you will. And so let's finally come over here and write our piecewise defined expression for m as a function of x. And so here I'll say m as a function of x is equal to, well, over the first 2/3, it's this relationship here, negative 500x squared plus 5,333.3 repeating x, and C1 went to 0. So quickly write that in, negative 500x squared plus 5,333.3x. And again, that's good between 0 and 8. And then the other third, between 8 and 12, is m2 of x. And so I've got the form, slide this over, you can see to the left here. The slope we said was negative 2,666 and 2/3 x, or negative 2,666.6 repeating is the slope. Okay, so that times x, and then the y-intercept to complete our linear function is 32,000. And we have here, that was between 8 and 12. And all those are less than or equal signs because I don't have any concentrated moments that are causing any discontinuities. And so at this point we've arrived at where we need to go. I guess one other thing I could make in here just to stay consistent, make sure that nobody's lost on units. Here x will be in meters and m will be in Newton meters there. And so now I believe everything is looking good. So we've got our two plots that we were after, the internal shear force, the internal bending moment. We've able to write them in nice piecewise defined expressions. One other thing I've gone ahead and done is got into Sage here, that open source online computer algebra system. And in blue here are the plots of the shear force, and in red are the plots of the bending moment here. And you can see the discontinuities that Sage is not showing, where we're basically dropping here at x equals 5 1/3 down to the negative 2,666 and 2/3, which actually I've got an error here. Let's go ahead and fix this. V1, I know exactly what I did wrong here. I stopped at 5 1/3 and didn't go down to x equals 8. So there we go. Fixed it on the fly. Basically what I mistakenly did before was I stopped plotting it right here, which is where it crossed the x-axis, but of course that is not where V1 ends as far as the domain, because that's exactly what we wrote right here. It said, hey, it goes all the way to 8 meters, which is where the distributed load is actually stopping. And so now that is the corrected internal shear force in blue plot and the internal bending moment in red plot there. And so thank you for watching the video. Hopefully you will find it helpful when you're working with your own problems, drawing shear and bending moment diagrams with distributed loads. And so thanks again for watching the video.